Hi ladies and gentlemen, this is Mr. Green again. This is another in my series of lessons on geometry. What we are working on Unit 4, and we're going to take up the topic from a different perspective. We've been looking at what the angles that are formed and how those angles are related to each other and how we can find the measure of those angles. We now want to look at finding some lengths and finding the length of some of the sides and some of the lines that are associated with circles. So we're going to look at that today and see if that can make some sense, okay? Don't forget, make quiz corrections if you need to. Don't forget due dates. When things close, can't open them back up. You need to make certain you don't have any zeros in your grade book. That's the worst thing you can do. Okay, so a tangent segment is a segment of a line that is tangent to a circle. So if I've got this tangent line right here, J, it's tangent to the circle Q at point A. It's tangent, only touch it at one point. Then a tangent segment would be a part of that line that is just the line segment A to P in this situation, is what they're looking at. That would be a tangent segment. Okay? It's just a tangent, a segment of a line that is tangent to a circle where one of the points on the tangent segment is on the circle. Okay? So it has to be that point of tangency. It's what it has to be. So let's look at how can we use that. Well, tangent segments are going to be equal for a circle. Actually, if you want to look at the truth theorem, it says that a circle, or any circle with the same radius, and you have tangents, the tangent segments are going to be congruent. That's interesting. That means that AP is going to be equal to BP down here. They're going to be congruent to each other. That means they have the same length. Okay? How is that helpful? Well, if I'm given an equation for AP like this one, 3x plus 4, and for BP, x plus 16, I can set those equal to each other. What do I mean set them equal to each other? I can say that 3x plus 4 equals x plus 16. Then using our algebra skills that we've got, we subtract the x from both sides. We get 2x plus 4, x plus 4 equals 16. Subtract the 4 from both sides, we get 2x equals 12. X is equal to 6. We found what x was. That doesn't tell us the length though. If I stick that 6 into either one of these, so 6 plus 16, that's 12 and 10, 22. I found that the length of this segment, BP, is 22. That means that AP will be 22 as well. And just to show you, that's what they came up with as well. Cool? Hopefully you guys see how that has worked. If you can't read my writing, don't worry, it's right over here. It's the same thing. Pointer. It's right over here. You can't. It's done the same way. Okay? And I'm sorry, my writing's kind of messy. That's why I give it to you typed out form like that. Okay? So let's look at what if they're chords that intersect. Can we find the lengths of these chords in here? Well, yes, the chord segments are the segments from the side of the circle to where the two chords intersect, and then from that intersection back to the side. This AE would be one chord segment, EB would be another chord segment, DE would be a chord segment, and EC would be another chord segment. And the theorem states that if we multiply on one line the chord segments together, they're going to be equal to the other chord multiplied together. It's an interesting theorem. So let's look at it and see what happens. AE, we got here 2x plus 2. And for EB over here, we got 6. So I'm going to multiply those together, and I'm going to get 12x plus 12. And for CE here, we've got 4x. And for DE, we've got 4. And so I'm going to multiply those together. They're going to be equal. 4 times 4 is 16x. So if I subtract the 12x from both sides, I'll get that 12 is equal to 4x, or x is equal to 3. We found what x was. Doesn't help us a whole lot because what they want to know is, what's this? What's the line segments, right? They actually want to know what AB is. So 2 times 3 is 6, plus 2 is 8, and 8 and 6 are 14. So AB is going to be 14. And CD is 3 times 4 is 12, plus 4 is 16, so 16. So I'm saying that the line segments are 14 and 16. And that's exactly what they came up with as an answer there. I want to show you what they did. They said AE times this, CE times that. Well, 2x plus 2 times 6, 12x plus 12. That's what I had right here. 4x times 4, 16x. That's what I had right here. They subtracted the 12x. They got the x is equal to 3. That's what I had right here. To find AB, they added AE and EB. Well, AE is going to be 8 plus 6. Where'd the 8 come from? 3 times 2 is 6, plus 2 is 8. Plus 6, that's what EB is. 14 is your answer. And CE plus ED. CE was 4x. 4 times 3 is 12. Plus the 4 for the other one, that's 16. That's how we found both of these two line segments there, by using the chord segments and multiplying them together. Okay? So let's look at another one. What if we had secants? Well, secants intersect outside of the circle. Okay, because if they intersected inside the circle, we just look at the chords and do it the way we just did that last one. So the only time we're going to look at secants is when they intersect outside the circle. And there's a secant segment is referring to any segment that has at least one of its points on the circle. Okay, so AB is a secant segment because it has both its points on the circle. AC is a segment because it's got A on the circle. BC is a segment because it's got B on the circle. Okay? Any of those any way you want to label those would be secant segments. There is a very interesting theorem here, and the theorem is not hard to remember. The theorem states that the whole times the outside. That means the whole secant segment. That means from A to C times the outside portion, B to C. So these two secants intersecting on the circle, whole times the outside will be equal to whole times the outside. Okay, that's the way I've always remembered this. Whole times the outside is equal to the whole times the outside for two secants intersecting there. Really easy to do. Okay? So when I look at that, I've got AC is 10. That's the whole thing, 10. Okay? And BC is 8. That's the outside. So the whole times the outside is going to be 10 times 8. That's going to be equal to this other one down here. EC, that's the whole thing, 2x plus 2, outside, 5. That's going to be 10x plus 10. Okay? So if I subtract the 10, 80 minus 10 is 70, is equal to 10x. So x is equal to 7. And I've solved it for x, which is what they were wanting me to do in this problem. Okay? But if I were trying to find what EC was here, I would take that 7 and put it back in here. 7 times 2 is 14, plus 2 would be 16. So EC would be 16 in this situation. And since DC was 5, that would make this one over here 11. Okay? Now I want you to recognize these are not necessarily drawn to scale. Because AC is 10 and BC is 8, that would make this one 2. Look at these. Do they look like they're the same length? Pretty close. Then how can I say one is 11 and the other one is 2? Because we're solving it using the equations, not using our eyes in this situation. The eyes are just showing us what type of a problem it is. It's the secant segment problem. Okay? So you got to be real careful with it. You can't look at it and say, oh, it looks like it'd be this. That will get you the wrong answer every single time. Okay? This is the correct answer here. Okay? And yes, you can see I take the whole segment and I subtract what I know, one of the parts I know, I can find the other one. That comes into play in some of the problems you will be working. Okay? So, the only other situation that we might run into might be a tangent and a secant running into each other. We've already looked at tangents and we said that the tangents were going to be equal in both situations. But in this situation, a secant, we've got that whole times the outside that we can look at. So we've got EB times DB. We can look at that. But I don't have an inside over here. I don't have an outside for my tangent. So how would we work with that one? What they do is they say, well, you know what? Everything is outside. So if you said the whole thing, that'd be AB times its outside portion, which is AB. That's actually AB squared. So it is actually the same equation. Whole times the outside is equal to the whole times the outside. That's what you just have to remember. So if I'm given this problem, it says that AB is 12. Well, 12 is the whole thing. It's also the outside. So 12 times 12 is 144. EB, that's 18. It's this thing here. And DB is the outside. It's 3x minus 4. I'm going to multiply 3 times 18. That's 54x minus 18 times 4, 3672. So if I add 72 to both sides of this, I will get 216 is equal to 54x. And if I divide by 54, I'm going to get that x is equal to 4. So I found what x was. If I plug it back in, 3 times 4 is 12 minus 4 is 8. So dB is 8, right? And since we knew that EB was 18, this one over here is 10. See how your eyes are deceiving you here a little bit? They're not quite giving you the right answer. But that's one of the things you have to be aware of when you're looking at these type of problems. Okay? Don't trust your eyes. Look at it to see what kind of problem it is, and then solve it based upon that type of problem. Don't try to guess at it by looking at the sizes. Okay? Having said that, I appreciate you guys always letting me know that you're in geometry and what section you're in. It helps me answer your questions quicker. So, if you make certain you let me know that, I'll look forward to seeing you next time we're talking. Bye.